So in this last section, I gave you a whole bunch of techniques to find exact solutions for rational roots. But then the question occurs as well, what if you don't have rational roots? What if they're not rational? How do you do that? Well, it's much more difficult to find them. So instead, we will approximate them. So let me give you some techniques for that. Approximating, so section 5.4, approximating irrational roots of polynomial equations. So suppose that f is continuous. So what does it mean to be continuous? So f is continuous at a if f of x approaches f of a as x approaches a. So you can think of it as follows. F is continuous at a if you can draw it without having to lift your pen off the tablet. So as x approaches a, the y values approach f at a. F is continuous on an interval I if it's for all values of a in the interval I. A continuous function maps open sets to open sets. A continuous function maps compact sets to compact sets. So a restatement of that is the intermediate value theorem. If f is continuous on a closed interval, AB, of course, A is assumed not to equal B, so it's actual non-empty closed interval. Then let C be a number between f of A and f of B. Then there exists a number D between A and B such that f of C is equal to D. So visually, suppose you have some continuous function on closed interval A to B. Pick any point C in the interval A to B. Pick any point D between A and B, between f of A and f of B. Then there exists some C between A and B such that f of C is D. So if you start here, and you end here between your start point and your end point. Polynomial functions are continuous everywhere. So let's do the location theorem. Suppose f is a polynomial with real coefficients. Suppose that f of A and f of B have differing signs. Then there exists some C between A and B such that f of C is 0. So if you start out at some point and you end up another point where you have a differing sign, then somewhere in between you had to cross the place where you were equal to 0. So since you went from positive to negative or negative to positive, somewhere you were equal to 0. So the bisection method, done around 2000 BC by the Babylonians, which said pick some A0 and A1 such that f at A0 has a different sign than f at A1. Compute the midpoint between A0 on A1. Call that A2. F at A2 has a different sign than F at 0. Then you replace A1 by A2. If F at A2 has a differing sign than F of A1, replace A0 by A2, and you repeat it until F at A2 is sufficiently small. So you're within some tolerance of how close you want to be to your root. This will work if there exists an A0 and A1 such that F is continuous on the closed interval A0 to A1, and F of 0 and F of 1 have differing signs. So if you start out where you're on differing signs of the on differing sides of the x-axis, so the idea is as follows: you start at differing sides of the x-axis, you look at halfway in between, you pick where you're still at differing signs, and then you do the midpoint again. You pick you're sufficiently close to your root. So let's do this. So first note, maybe I'll sort of do it here. So let me just put in my number here. 2x cubed, so let's go up here. 2x cubed let's clear everything because it's 2x cubed plus 17x squared plus 31x minus 20. So let's figure out what happens at -1 for this. And at 2. Okay, so -136 and -36 and positive 126. Okay. So P at -1 is equal to sorry, I'll have to, so P at -1 is -36. P at 2. It doesn't really matter how big these are yet. All I want is that they differ in sign. So one is positive, the other is negative. So now what I want to do is, here, let me give another page, is find the average of these two numbers. Let's insert another page. Okay, good. So I have another page here. So let's just find the average of these two. So -1 plus 2 over 2 is just 1/2. Okay, so now let's check P at 1/2. So just the midpoint. So let's just check the midpoint here. So if I do that, so let's plug in 0.5. So at 0.5, I am, come on, at 0. 2 minus 1 I'm at 0. Okay, well that was, okay, so I found the root. Okay, so it turns out I accidentally found the root. Am I really at a root at a half? Okay, so I don't think that's a true statement. Let me just check this for 1 second. X cubed plus 17x squared plus 31x minus 20. Minus 20, yeah. Okay, so at a half, I'm guessing I'm at 0. Okay, so, oh, let me just check if that's not really 0, but a small number. So has at least one, so find the number. So the answer is 1/2. Okay, let me use the bisection method to find the following values to the nearest tenth, a negative root of this. Okay, so let's find a negative root of, clear this, x cubed minus x plus 2. Okay, so let's try to find that. Okay, so let's look at 1 is going to be a negative root. So I want, say, a negative 3, say 2. Okay, and a 0. Okay, so if I look at negative 2 and 0, so f at negative 2 is negative 4. F at 0 is 2. So this is negative, positive. Okay, so now, so x0 so I'll let x0 equal negative 2. Let x of 1 equal 0. Okay, so now the midpoint, negative 2 plus 0 over 2. That's a negative 2 over 2 is a negative 1. So that's the midpoint. So let's figure out f at negative 1. Okay, so let's figure out f at negative 1. So at negative 1, I get, a little slow, at negative 1, I get 2. So at negative 1, I get 2, which is greater than 0. So I have to pick the one with opposite sign. And so x of 2 is negative 1. Okay. So now I'm going to have to find a midpoint, negative 1. That's negative 3/2. Okay. So now, let's look here at okay. Let's look here at negative 3/2. So negative 1.5. It's still positive 0.125. Okay. So x of 3 was negative 1.5. I'm still going to have to do 2. Okay, so midpoint between these two numbers is a negative 1.75. So that's going to be x sub 3. So x sub 4 is negative 1.75. Okay, negative 1.75 gives me a negative, that's a negative 1.6. Okay, negative 1.609-ish. Yeah. Well, that's probably actually correct value. So it's a negative 1.609375. Okay. We're getting slowly closer. So now I have to find the midpoint between a negative and a positive, which was 1.5 was the other one. So 1.5 and 1.75. The midpoint between those is 625. That will be your x of 5, negative 1.625. And so let's look at f at that value. Still not at 0 yet. Okay, so let's look at that. So negative 1 point, oops, I'm going the wrong place. Negative 1.625. Negative 6.666. Okay. So this is negative, approximately. Oh no, that's a 2.5. Probably that's the correct one. Negative 0.666015.625. Okay, still negative. So midpoint between negative 1.5 and 1.625. And I want to get this to the nearest tenth. Okay, so I'm not sure if it's 1.5 or 1.6. Okay, 1.5 or 1.6. Okay, so this is 1.5625. Okay, and that'll be your, okay, so now let's look at f at negative 1.5625. So x sub 6 is negative 1.5625. Okay, let's look at that. Negative 1.5625. Still negative. Oh, but it's getting closer. Okay. negative approximately that number. So it's negative 0.25, getting closer, 219.726563. Okay, so still negative. I guess I should have, these were obviously negative. Should have said that. So greater than 0, these were still negative. So I still have to pick the positive, which is 1.5. Negative 1.5, 1.625. Okay, still the midpoint of those. 1.5 and, oh no, 1.56. 1.5625. Okay. It's 1 point. So it's pretty, oh, then this is going to be a 1.5 now. 1.53125. So the nearest tenth, I now have had it, because now it's going to, even if you average these two, will be that. Takes a little while, but I found that my root is approximately negative 1.5. So I have the to one decimal place is 1.5. So that's my approximate root. Okay. Just one last minute, we'll be done with this section. Derivation. Let P of X equal the sum, K equaling 0 to N, then A sub K, X to the K, then the derivation, P prime, is just the sum, K equaling 1 to N, of K, A sub K, X to the K minus 1. So if P sub X is equal to 3x squared minus x plus x cubed minus x plus 2, then the derivation would be bring down to 3. So it'll be a 3x subtract 1 squared minus derivative of x is 1 plus the derivative of a constant is 0. So it's 3x squared minus 1. So Newton's method says, well, suppose you have the slope of a line, m equals y2 minus y1 over x2 over x1. So suppose you want to find a solution to the root of some function, y equal f of x. Then you look at this derivation, which is the slope of the line here, this tangent line. And you start at some point, arbitrarily, take the line, find where that line intersects the x-axis, take that as x1 as your next point, and then go from there. And so you start with this x1, and then find the tangent line, see where it intersects, that's your next x, and then keep going on with the same sort of process. And so you start out at the point x n, f of x n, and well, this point of intersection is x of n plus 1, 0. And the slope is f prime at xn. And so f prime at xn is the difference between the y's, so 0 minus f of n, divided by the difference in the x, xn minus xn plus 1 over minus xn. Cross multiply. So you get x of n plus 1 minus xn equals minus f of xn over x prime xn. Add xn to both sides. So the way that you get to the next point, xn plus 1, is you just use the formula xn minus f of xn over x prime xn. So you choose x0 arbitrarily, but just be sure that f prime at x0 is not 0. So let's do one last problem, and that's it. Oh, which is this guy. Find the negative root of x cubed minus x plus 2. And so f prime is 3x squared minus 1. Okay, so let's do that. Notice it took a while to get the other root. And so recall, that x sub n, okay, x sub n plus 1 is xn minus fxn for f prime xn. Okay. Okay, so let's just plug that in. Okay, so there it is. Let's get out of this. Go to y. Okay, clear that out. So it's x minus f of xn. So that's just, what is it, x cubed minus x. Oh, wait, clear that. That seemed to have had something else there. So the root of, let me just check, x cubed minus x plus 2. Okay, so it's x cubed, so it's x minus, parentheses, x cubed minus x plus 2 divided by 3x minus 1. 3x minus 1. Okay, good. So that's what that is. So now, let's arbitrarily pick something. Let's say negative, let's pick negative 1. So let x0 equal negative 1. Let's figure out x of 1. Okay, so let's plug in and figure out x of 1 is. So I plugged in negative 1. Okay, so it is negative 0.5. Let's figure out x of 2. So figure out x of 2. Negative 0.5 gives me negative 0.45. Equals 0.45. Hopefully it doesn't go to the other root. Okay, so that's 0.45. This gives me, I guess I should have gone there, negative, wouldn't you notice? Wouldn't you know that? Okay, which gives me negative 4.238. Let me just see something for 1 second. Okay, come on. Xn minus xn. Okay. Eight, 9, okay, so let's see why it's just kind of weird that it's oscillating around a little bit. Negative 4.2389285714. Okay, so I'll just sort of say you keep plugging in these values and they'll converge to a value and why it's not converging. Oh, it's probably because I plugged in the wrong, let's see, x squared minus x. Okay, so I'll just x minus x cubed minus x plus 2. Yeah, that's error right there. It's 3x squared. And for some reason, it didn't put the square there. Okay. Okay, so get back. This calculates a little, well, the whole computer's slow. X. 3x squared. Okay, good. There it is. Okay, so sorry about that. Okay. Okay, so let's do this. So -1 gives you a -2. Okay. -1 gives you -2. And -2 gives you this should convert very quickly. -1.63. Okay. Let's do that. -1.63. Should give you just about 0. Okay, -1.53. Okay, 3. -1.533039200521. So we're already at the, oops, we've gone more than one decimal place. -1.533039200521. That gives you the same, virtually the same number. -1.52 144 14651, and I bet you if you plug that number in, you probably get the same number out. -1.52 144 14651. So we're to several decimal places already. So x of 5, negative 1.5, 21379, 7097. So my approximate answer is negative 1.521 and rounding to 4. So to 4 decimal places and with less work actually than the other one. So that